Hello everyone, and thanks for joining this webinar. My name is Timo and I'm an application engineer at Speedgoat. In today's webinar, I will show you how to use Speedgoat real-time testing solutions to accelerate development of autonomous systems and other robotics applications, like industrial automation or vision processing systems. We'll start with an overview of some of the main challenges we see in the area of robotics and autonomous systems. Then we'll go over multiple examples and workflow demonstrations using Speedgoat target hardware and Simulink real-time. I'll start with data acquisition from an IMU, followed by controls prototyping for a vision-guided robot. We'll see how you can design a digital twin for virtual testing. And lastly, an example for deployment and instrumentation. In the end, I'll wrap it up by giving you a full overview of the combined Speedgoat and MathWorks solution for real-time testing and give you some insight into how our customers apply these tools in the field. Let's start with an overview of the main driving industries for robotics. Although there are many other applications, we see the biggest interest in the following fields. Firstly, the medical sector. Robot-assisted surgery is a huge topic, here illustrated with a heart surgery robot by our customer Corindus. Rehabilitation equipment also benefits from robotic systems developed with Speedgoat hardware, like the ankle-foot prosthesis by Humotech. Another strongly growing industry is mobile robotics. Research facilities around the world are using Speedgoat real-time systems to develop autonomous mobile robots operating in water, on land and even in space, using all kinds of locomotion methods. Industrial robots used in manufacturing make processes continuously more efficient, reliable and safe. For example, HOMAG uses Speedgoat machines to develop cutting-edge control algorithms for CNC machines. And University of Agder is training the next generation of mechatronics engineers using a large-scale hydraulic crane controlled by Speedgoat. The last megatrend I'd like to mention is the development of autonomous transportation. Speedgoat customers such as Tata Motors are building autonomous vehicles to use existing road infrastructure, while for example our partner Technical University of Munich participates in the Hyperloop Challenge, developing entirely new, revolutionary ways of transportation. All of these areas have some challenges in common. They typically require you to develop and test complex control systems, to control many degrees of freedom with high precision. Maybe you want to use modern methods like model predictive control or reinforcement learning. To achieve automation, there's often a large amount of sensor data which needs to be fused and processed in real time. The data is also often transferred using new communication protocols. Maybe you need to incorporate cameras or LiDAR, or want to set up data distribution service between different devices. Lastly, many areas require strict safety and certification requirements to be met. So you need to perform rigorous testing as development progresses. Keeping up with the pace of innovation is a challenge of its own. Leading engineering companies have to deliver smarter and more power-efficient products to stay competitive in such a dynamic market. To address these challenges, robotics engineers have been progressively relying on model-based design and real-time simulation and testing to efficiently design, develop and test their new embedded controllers. Before we look at more hands-on examples of how to use real-time simulation, let's quickly discuss the base architecture of robotic systems. Most generally speaking, all systems consist of a controller and a plant. An input signal is applied to the controller, which controls the signal fed to the plant. And in a closed-loop system, the output is connected back to the input. The controller could be a microcontroller in a drone, a PLC for a factory robot, or an ECU for an autonomous car. During development, you can use the Speedgoat real-time target machine as a prototype controller and refine your algorithm controlling the real system. This is called rapid controller prototyping. In a later step, you want to test your embedded controller extensively in realistic scenarios. You can do this by connecting it to the Speedgoat target machine working as a hill simulator, running a digital twin of the plant. This allows you to test earlier, automate your tests, and cover edge cases, which would be dangerous using the real plant. As you can see, the real-time target machine forms an essential component in prototyping a plant controller system. Let's now look at our first example of a workflow needed before you even start working on your controller. When starting real-time testing, you often need to integrate new components, like sensors and actuators, and set up the required interfaces. Perhaps your goal is developing a UAV attitude controller, a camera stabilizer, or a new multi-joint legged robot, and this requires you to interface with inertial sensors. I'd like to show you how you can combine Simulink with Speedgoat hardware to support you on such tasks. More specifically, we will connect to an inertial sensor, perform spontaneous real-time measurements and data pre-processing. I'm using a 9-axis inertial sensor which communicates over an I2C protocol, a common serial interface. To set up and test the sensor, I use a Speedgoat unit real-time target machine, our smallest form factor. So let me switch to MATLAB and Simulink to show you how this works. In the Simulink model, you can see on the left side the subsystem where we take the sensor readings from the IMU. To communicate with the sensor, I'm using the IO397 configurable I/O module. Configurable means that it can easily be reprogrammed with configuration files that enable different functionalities, such as the I2C interface which I'm using here. For communication, we need the device ID and register addresses to read from or write to. I set up 2 write signals here to configure the sensor, and then we want to continuously read out 14 bytes of data containing the accelerometer, temperature and gyroscope data. I have already selected these output signals for logging to the simulation data inspector. To log additional signals, just click on it and choose Log Selected Signal. My model is already configured for real-time execution, but for any other Simulink model, you could simply go to the Apps tool strip and select Simulink Real-Time to adjust the needed settings. Namely, this will configure the model to use a fixed step solver and generate code for Simulink real-time targets. Directly from the Simulink tool strip, I can now click Run on Target, which will compile, deploy and run the model on the Speedgoat real-time target machine. While the model is running in real time, I can observe the logged signals in the simulation data inspector and verify that we are in fact getting sensor data, and the signals reflect the movement of the sensor. Aside from the simulation data inspector, you can also use specific Simulink blocks to analyze your signals, like a scope or a spectrum analyzer. Similar to SDI, these blocks allow us to visualize the data while the model is running. The scope has many functionalities similar to an oscilloscope, like cursor measurements, bilevel measurements or triggering. The spectrum analyzer could be useful, for example, to analyze the noise in our IMU signals and design a filter to improve the signal-to-noise ratio. I hope this illustrates how quickly you can run your models on Speedgoat targets directly from Simulink and connect with sensors and other hardware using the Speedgoat I/O block set. Allow me to share the success story of our customer Precise, who has used Speedgoat and Simulink Real-Time to develop the world's first eye surgery robot. While constructing a model of the robot's kinematics and dynamics, the engineers use data acquisition workflows for system identification. They use Speedgoat target hardware with EtherCAT interfaces to excite the robot's motors and measure the response. The team then used the same target hardware to develop a controller model that processes input from a joystick and around 60 sensors and generates motor commands in response to the surgeon's movement. So they followed up data acquisition with rapid controls prototyping, which is what we will look at in the next example. We'll work with a prototype controller deployed to a Speedgoat machine, and the plant will be an actual industry-grade robotic arm with a gripper. Let's imagine a scenario where you develop a factory robot, which is used to detect and remove defective or faulty parts from a conveyor belt. Inspection of the parts is done using images from a gigabit Ethernet camera, and the defective parts are detected with computer vision. The Speedgoat performance real-time target machine will handle this task, as well as generating movement commands for the robot to pick and remove the respective parts. The communication interfaces in this example are gigabit Ethernet for the camera input and EtherCAT, a widely used industrial protocol to control the robot arm. This is my hardware setup for testing. As objects, I'm simply using differently colored balls, where the red ones represent defective parts which need to be removed. The camera is mounted in a fixed angle overhead, on the opposite side of the robot. Let's first see how the computer vision algorithm works on a very high level. The overhead camera image is cropped to the area of interest, and thresholding on an intensity image is used to remove the background. An algorithm for connected component analysis, or CCA for short, then calculates the bounding boxes and center coordinates for each object, and we filter them by primary color to detect the red balls. Finally, we transform the detections from the pixel coordinates into the robot's frame of reference and send them down the data stream. The object detections are then fed into the supervisory controller for the robot arm as planar X and Y coordinates. The move commands generated by the controller are sent to the robot using EtherCAT transmit blocks from the Speedgoat I/O block set. I won't go into the details of the inner workings of the controls, but it basically consists of a state machine which goes through all the necessary initialization steps, then keeps the robot in a neutral position until we trigger it to pick an object. Once we do that, a trajectory to the object is generated, the robot moves to pick it up and puts it in a container to the side. I have also added 2 dashboard indicators to observe the state of the system and a trigger button. I'm already connected to the real-time target machine, as we can see in the top left corner of the Simulink tool strip. So I just click Run on Target and the model is compiled, loaded and executed on the target. You can see the robot on camera here, and the dashboard shows that it is initialized and objects have been detected. So when I click the Pick button, the robot will move to the first object from the list and remove it. I simply click the button again while objects are still being detected. Of course, this could be fully automated later, but for testing it is handy to have these controls. Now you might still wonder how the target machine is able to process high-resolution video data in real time. The vision algorithm is actually running on an FPGA, our real-time vision processing I/O module. It supports various vision interfaces, such as USB UVC, Gigabit Ethernet, SDI and HDMI. With clock rates in the range of 100 MHz, it allows to process high-resolution, high frame rate video streams in real time. It can read in or emulate multiple cameras simultaneously, record and replay files, and is fully Simulink programmable. The algorithm I'm using in the robot example is based on a shipping example from MathWorks Vision HDL Toolbox, which I am linking here. This model is a bit too complex to discuss here in detail, but I encourage you to take a look for yourself. From this Simulink model, we can then generate HDL code to deploy to the FPGA by simply going through the HDL Workflow Advisor. This is where we map Simulink signals to hardware interfaces, define clock rates, and so on. It's a simple step-by-step process, allowing you to seamlessly integrate high-speed vision processing into your real-time tests. And this wraps up our vision-guided robot example. To conclude the RCP section, I'll share a customer story from the Soft and Micro-robotics laboratory at MIT. The researchers are using artificial muscles to power insect-like aerial micro-robots. As the size of these robots shrinks, the dynamics become faster, therefore requiring higher sensing and control rates. With 400 wing flaps per second, the feedback control needs to run at 10 kHz frequency. The researchers model and simulate the dynamics at different fidelity levels to identify the optimal wing shape. Various experiments are performed to identify the mapping from actuator inputs to lift, resulting in an accurate flight dynamics model. This is then used to test new control algorithms in closed loop without risk of damaging the real robot. And finally, the controls are seamlessly tested using the real robot by interfacing the Speedgoat machine with a Vicon motion capture system and sending actuator commands to the robot. Up next, I would like to discuss an example for hardware-in-the-loop testing. This is where you test your production controller against a digital twin of your plant. Some of the main benefits of HIL are: you can test in a safe, yet completely realistic environment. You avoid a lot of logistics overhead from only testing with prototypes. You can even test when the real system is unavailable, and therefore start testing earlier. Virtual testing can also be fully automated. You can go through various test cases and accumulate hours worth of test data without requiring any user input after the start command. And last but not least, you can inject faults and test edge cases of your controls problem without risk of damaging the real system. A main challenge here is often how to create a realistic and accurate digital twin model of your real system. Let's look at an example for our Mecha 500 robot. When you buy robotic components off the shelf, you typically get the CAD 3D models with it, so I'd like to show you how you can use those for creating a SimScape model. For the Mecha 500 robot, the CAD data is even directly included in Robotic's system toolbox, along with many other 3D models. One simple command loads the data, and we can already view a 3D representation of the robot. Using the function smimport, we can then generate a SimScape multibody model from it. Here we can see the generated links and joints, adjust parameters such as inertia and mass distribution, or let MATLAB automatically calculate these values from the parts geometry. When we simulate this model, the Mechanics Explorer shows us a 3D visualization of the scene. So this is just a blueprint model with no controller yet, but it can quickly be used to perform kinematic or dynamic simulations and develop motion planning and motor control algorithms. To get a head start in adding the controls, we can, for example, refer to one of the many examples shipped with Robotic System Toolbox. The example, Model and Control a Manipulator Arm with Robotics and SimScape, seems perfectly suited for this. When we open the model, we can find a similar SimScape implementation of a different robot arm, which we could replace with the one generated from our CAD model. Then we have models for gripper control, joint torque control, and trajectory planning, which we can explore, customize, and adapt to our needs. In a recent master thesis project sponsored by Speedgoat, the student implemented such a digital twin model of the Mecha 500 robot to test his controls for use of the robot as an automated touch device tester. He enabled the robot to automatically perform a full factory test of touchscreen devices, such as a smartphone. We will come back to this application in the next example, so keep this in mind. But first, I'd like to share another interesting customer success story involving digital twin HIL simulation. Our customer Leclanche develops lithium-ion battery packs for automated guided vehicles for factories and warehouses. This includes optimizing battery management systems, state of charge and state of health estimation. But running tests on real batteries has limited coverage, is very time-consuming and prone to errors. Another drawback is a lack of preliminary testing possibilities, which means bugs can often only be found in later development stages. Leclanché decided to address these issues with a hardware-in-the-loop test bench from Speedgoat. With full cell emulation and detailed battery models built with Simulink, they can now automate many of their tests and test edge cases, faults and disturbances safely in simulation. This cut testing time in half, while increasing test coverage and allowing for much earlier bug detection. To learn more about how HIL can support robotics controller testing, I recommend you check out the following webinar by our colleagues at MathWorks and Siemens, which outlines how HIL simulation on Speedgoat hardware can be applied as an effective means for virtual commissioning of a Siemens PLC for a robotic arm. Now for the fourth and final application example for today, we'll look into deployment and instrumentation. At this stage, you may want to open up access to your real-time application for non-Simulink users, like test engineers, and provide them with customized user interfaces. Let's revise the example of our robotic touch device tester. At this stage, you finished fine-tuning of the supervisory controller to control the 6 degrees of freedom manipulator using the Speedgoat with EtherCAT interface. It is now time for you to design a user interface that will be later used by operators to run automated test routines. In this case, you can use MATLAB App Designer and its integration with Simulink Real-Time to quickly create standalone user interfaces. The Simulink model is quite similar to the motion control part from the last example, with different trajectories. But what we will focus on now is the user interface built with MATLAB App Designer. Here you can see the App Designer window and the app I have created so far. This is the design view, where we see a graphical preview of our user interface, which we can modify with just drag and drop. There is a UI access plot where I will display the phone screen image, and then we have some buttons and status lamps to interact with the robot. Of course, we need to code what's going to happen when each button is pushed, so this is done using callback functions. We can jump to the callback function by right-clicking the UI element and select the callback, which will switch over to the code view. The grayed out parts of the code are automatically created when you add an element in the design view, and we only need to add the core functionalities. Here we are setting some parameters on the target machine using the setParam command. Similar for the lamp indicators, we have functions to set the color based on status changes. What's still missing though are some buttons to interact with the target machine itself. In the App Designer library, we can find some pre-built buttons from Simulink Real-Time. These require no coding at all, taking a lot of work off my shoulders. I think I will need a drop-down menu to select the target machine and a start button, of course. And before we can start, we also need to connect to the target machine. And finally, it's always a good idea to have some status indicators. As said, these buttons work without any additional coding, but sometimes you still want to add additional functionalities. In that case, you can still add another callback function. App Designer then creates the functions tab, and you can simply add everything else you need the function to do. When we're ready to test our app, you just click the Run button and App Designer will compile and start your app. So now, let's see our robotic touch device tester in action. On the left side, you can see the screen capture of the MATLAB app I just showed you, and on the right, a camera view of the robot. We only have to click a few buttons now, and the robot will do all of the work for us. First, we start the real-time application on the target computer, and the robot will automatically perform a homing movement. Then we proceed with telling the robot to unlock the test phone with the factory default PIN code. Afterwards, we select to open the test menu, which is done by entering a standardized sequence on the dial screen. And finally, we run our test function, which will start and execute the touchscreen test. On the direct video feed from the phone, we can clearly observe if all the checkboxes are turned green. This check could of course also be automized in a later step using image processing. With the test successfully completed, the phone goes back to the test menu and we will go back to the presentation. Now let's also chat about using a real-time target machine as embedded controller for your prototypes and smaller series. You may ask why, and that's totally fair. So first, you get the closest connection possible to Simulink to implement controller changes. Second, you have less or no constraints on your compute resources, especially when you are trying different control concepts. Third, a real-time target machine ensures deterministic real-time behavior of your controller, which desktop environment can hardly provide. Overall, it's not only great for testing and verification and validation, but also leads to reduced costs and risks. For example, we have a customer that uses real-time targets for robotic support systems, as depicted on the screen. But it is also suitable for many other applications. So, now you have seen different examples, ranging from data acquisition to controls prototyping, hardware-in-the-loop testing, and deployment and instrumentation. Let me now give you an overview of how Speedgoat test systems, together with MATLAB and Simulink from MathWorks, form the most powerful and unified test platform. I will point out key benefits of this solution, the hardware enablers and software enablers. Now, why work with Speedgoat hardware and Simulink real-time? In summary, and most simplistically, when you work in Simulink, there is literally no detour to get to your real-time application. It's practically the same. You parameterize your real-time application in Simulink and also deploy it from there. So Simulink isn't only your deployment environment, it is also your hub for all kinds of testing, including logging, instrumenting, and configuring your hardware to run. Simulink and Speedgoat development has been happening hand in hand for more than 10 years. Hardware and software are expressly designed for one another, so you won't experience any version lag. I have asked Jay Abraham, Group Manager for Real-Time and Verification Products from MathWorks, to share for us the MathWorks view on this collaboration.
Thanks for bringing this up. Happy to share the MathWorks view on how we work closely with Speedgoat to provide our mutual customers with a fully integrated and best-in-class real-time simulation and test solution. To enable this fully integrated software and hardware platform, MathWorks and Speedgoat engineering teams collaborate very closely. For every release of MATLAB and Simulink, we check that the products work out of the box with Speedgoat hardware. Furthermore, we ensure that the workflow leverages the power of model-based design. For example, being able to reuse tests from desktop simulation directly on the real-time target hardware. We also coordinate with each other's support teams to make sure that the customer experience is seamless. And you can be assured that our technical sales teams will support you throughout the evaluation and purchase process.
Thanks Jay for sharing this with us. Next up, let me show you the hardware enablers for your workflows. For the great variety of different robotics applications, Speedgoat offers a wide range of real-time target machines. For the highest power and flexibility requirements, we recommend the Performance Machine. It ships with the latest Intel CPUs and allows up to 50 I/O modules. The chassis is tailored for desktop as well as lab use. Depending on your compute tasks and the number of required interfaces, the performance machines are also designed for rack mounting. The mobile, baseline and unit machines are ruggedized, hence allowing being used in prototypes or moving vehicles of any kind. Yet they are powerful and allow for modular I/O expansion. The mobile can host up to 14 I/O modules, the baseline up to 7. Both offer an excellent trade-off between compact form factor, power and flexibility. Unit machines are especially great for controller prototyping of size and weight constrained projects, such as mobile robots and portable devices. One additional I/O can be added specific to your application. And thanks to the modularity and flexible design, customization of our machines to your requirements is always an option, as well as the specification and design of large-scale rack solutions. And on a side note, our customer Think2Brain, who is developing a personalized brain stimulation therapy for patients suffering from neuropsychiatric diseases, is using a customized unit machine as their deployment control device. They recently got confirmation that Speedgoat's ISO 9001 certification is interfacing with their IEC 13485, and they achieved certification of the use of Speedgoat as an embedded device in medical control applications. And no matter whether you are prototyping control strategies or testing controllers against your digital twins, hardware connectivity shouldn't be a hurdle for you. Speedgoat is supporting key protocols across all major industries. Some key mentions for robotics here are, for example, UDP, EtherCAT, CAN or serial protocols to interface with other devices. Analog, digital, SPI and I2C to connect with sensors, PWM generation and capture for actuators, and battery cell voltage and temperature emulation. More than 200 I/O modules are available and ensure that your workflows remain uninterrupted. Now for the software enablers, I want to emphasize that you get all of the capabilities built into MATLAB and Simulink, supplemented by the Speedgoat I/O block set. Maybe you are already familiar with some of these, but let me highlight the main capabilities MATLAB excels at with regards to real-time testing. You acquire and visualize real-time data from mixed sources and perform interactive analysis with minimal effort and no coding. You trigger specific signals and test profiles. You create instrument panels that make it easier to interact with your test application. You tweak parameters to influence performance and switch between testing scenarios. You pre-process data and simulate your complex physical systems in open or closed-loop manner. You author complex test scenarios and automate repetitive tasks. You co-simulate and interact with software environments of your choice. You deploy test applications and run them independently from the development or host computer. As I already mentioned earlier, you might also benefit from adding specialized toolboxes to your MATLAB and Simulink to simplify your workflows. Let's see some examples. Robotic System Toolbox provides Simulink blocks to easily design, simulate and test manipulators, mobile robots or humanoids. The use of these blocks simplifies tasks such as collision checking, trajectory calculation and inverse kinematics or dynamics calculations. For modeling multi-domain physical systems, you can leverage Simscape. Simscape offers optimized solvers for real-time simulation and is therefore suited for hill testing. The tool also allows you to automatically create models from CAD assemblies, which greatly simplifies the creation of digital twins. It seamlessly integrates with UAV Toolbox, Aerospace Block Set, Vehicle Dynamics Block Set or Powertrain Block Set, and Robotic System Toolbox, as needed per your application domain. You can also integrate data-driven techniques, automate parameter tuning using experimental data, train surrogate models, for instance using reinforcement learning and predictive maintenance toolbox, and deploy them as real-time agents to run on Speedgoat machines. One of the areas Simulink is most known for is of course simplifying controller design. From classical PID controls to model predictive motion planning, integrating perception and learning-based decision-making, to high-speed motion controls. MATLAB and Simulink support you in all of these areas and seamlessly run your application on Speedgoat target machines with I/O. And I'd like to emphasize one more time the extensive resources all of these toolboxes come with fully documented examples and reference applications to get you started quickly. Just as a tiny sneak peek, this could be generating code for object detection, model predictive lane keeping assist, battery cell balancing, automated testing of lane following control, UAV package delivery, simultaneous localization and mapping, or training a deep deterministic policy agent for adaptive cruise control. You can also find more resources online on many other areas you might be interested in. The QR codes on this slide refer you to more info on some topics I couldn't cover today. The use of native MATLAB interfaces to integrate Python, C++ or C# code, or control your application externally using those languages. A hands-on webinar on deep reinforcement learning to handle complex control problems. And the use of Gazebo or Unreal Engine for co-simulation to visualize your simulation live in 3D. You can do this either on Windows or on Linux, as Simulink Real-Time is fully compatible with both operating systems. If you'd like more information on any of these topics, please refer to these links or reach out to us directly. To conclude, I would like to come back to a previously mentioned customer success story and how they leverage the Speedgoat and MathWorks tools for real-time testing. Humotech, short for Human Motion Technologies, is a startup which emerged from academic research at Carnegie Mellon University. Let's hear it from their Vice President, Gabriel Forsyth.
Humotech's mission is to transform the way the world develops and uses exoskeletons, prosthetics, and other wearable machines.
The Caplex system is a wearable robotics platform for other innovators to develop upon. It involves physical wearable devices tethered to off-board actuators. It also includes a software component that controls the actuator in real time to regulate the torque applied by the wearable device.
The emulator creates the physical sensation of wearing different devices. So for users, you put on one emulator and try on a host of devices, switching from experiencing one device to the other in between steps without even breaking stride. Being able to compare two devices back to back makes the comparison for the user more precise. Those subtleties might be lost if there's 5 minutes between trying on one device and the next.
Whatever wearable device you have in mind, this sort of serves as a system where you can take that idea and just try it right then and there.
I also want to briefly emphasize how great a partner Speedgoat has been for Humotech, not only for supporting Humotech and building this wearable robotics platform, but also being a great tool for our customers. Our customers, like I said, include academic, clinical, commercial spaces where users and operators of the system have wide varieties of focus areas and technical skill levels. So we need the system to be both very accessible and very powerful and deep, and Speedgoat fits right in there. So hopefully this gives you a sense of what is possible with a Caplex system and how Speedgoat is helping to enable the future of wearable machines. Please feel free to reach out if you have any other questions or are interested in learning more. Thank you so much.
Thanks, Gabriel. That's really great to hear. After success with the initial laboratory-based system, the team sets its sights on a new portable version of the platform to enable experimentation in unstructured and real-world environments. Before we start with the Q&A, let me summarize 3 key takeaways of today's webinar. Prototype control designs faster and test them in real time without leaving Simulink using Speedgoat test systems. Reduce testing time and increase test coverage with hardware-in-the-loop testing. And get started quickly with real-world application examples and experience from Speedgoat. Thank you very much for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.